Cool. So that should be recording now. I'm doing it outside of Zoom, just in case anybody thinks that's weird. Sometimes when I record within Zoom, my computer decides to throw a bunch of green seizure-inducing flashes at people. So that's why you didn't hear the recording now thing. But legal disclaimer, we are recording this. Let's see here, and I need to share my screen so you guys can look at all the chemistry. Excellent. Okay, I'm going to open the floor up to any questions that you all might have, any particular topics that you want to go over. Let me hear it.
I have a question.
Mm-hmm.
So when you're naming the chemicals, how do you know to like put the parentheses for the transitional metals?
Well, you said it right there, actually. You only do it for the transition metals. So we can identify where the transition metals are by taking a look at our periodic table. This is the exact one that I'm giving you on your exam. If you want to study using this exact periodic table, you can go to your exam 1 quiz here, and then you should see it listed inside the description box. Your page will look a little bit different than mine because I'm an instructor, but these are the periodic table and polyatomic ions that you'll be given. So back over here, looking at this, the transition metals are, is it going to let me highlight? It's not. Everything from scandium over to zinc and then down to copernicium here. So this kind of rectangle in the middle, those are the transition metals. One of the ways that you can remember is that they are the transition between the two sets of main group metals. Our main group metals are these first two columns, and then any of the metals over here on the last 6 columns. And so the transition between those two groups of main metals are the transition metals. You do have to do the same thing for the inner transition metals as well. The inner transition metals are the lanthanide and actinide series. So basically this whole cutout rectangle down below, those also count as transition metals, and you'll have to specify with parentheses what the charge of the metal is. Did that answer your question, Samaya?
Yes, it did. Thank you.
No worries. Anything else, guys? Please do feel free to call out as much as you want during this. It's meant to be time for you guys to get your questions answered ASAP as they relate to the material. Let's see. Okay, well, no worries. I did prepare a little bit of stuff. We can go ahead and take a look at some problems here.
So I have a question on the molecular nomenclature homework.
Yeah. What's up?
So the question was the IUPAC name of H3AS.
Okay, H3AS. Any chance it had an aqueous symbol after it?
It does not look like it.
Okay, that's a little bit misleading then. I imagine the homework system wanted you to name this as an acid. The reason I can infer that is that it's one of the 3 types of nomenclature we go over in General Chemistry 1. And also, the hydrogen being shown first is usually a very good indicator that this is an acidic compound. And so, in order to name this as an acid, we usually show a little AQ symbol there after the name of the material. That means aqueous, literally, but it makes it very, very specific that this is a binary acid. All of the compounds that start with hydrogen have one other element and end in AQ are considered acids. So we can name this as a binary acid then. When we are naming our binary acids, we specify that it's a binary acid by including the word hydro first. Hydro. Then you take a look at whatever your root element is. In this case, it's arsenic. The root of arsenic would be arsen. And then all of our binary acids end in ic acid. And so hydro, arsen, ic, acid.
Okay. The test, will it display the aqueous symbol as well?
Oh boy, I sure hope I did that. I will double check. I'm pretty sure I did it correctly. I made the practice test from the stuff I gave you on the exam, and here I did include the aqueous symbol. So I think it's a pretty safe bet.
Okay.
But I will
Thank you.
double check on that for you. Thank you, Logan. Now, most of you probably noticed that I did a lot of saying binary acid. That's specifically to differentiate from the oxyacids or from the polyatomic acids. Our oxy/polyatomic acids have a completely different set of rules for naming them in order to help differentiate them from the binary acids. So when we say polyatomic or oxyacid, that's a clue about what is included in that acid. I'm including a list of polyatomic ions for you all on this exam. This is those. Polyatomic ions are ions which have multiple atoms in them, as the name suggests. You can think of these as kind of like a charged molecule or a ball of atoms that has a charge to it that is kind of just roaming around together as one complete unit. So in order to make a polyatomic acid or an oxyacid, you need to have one of these polyatomic ions as a part of that acid. Take, for example, here NO3-, that is the nitrate polyatomic ion. Finding that the name of the polyatomic ion is nitrate is necessary for us to name the acid. So let's say that I had HNO3. When you are making a polyatomic ion name into the name of its acid, I like to write down the polyatomic ion first. So this is nitrate. For our oxy/polyatomic ion acids, you don't include the word hydro. So for oxy acids, no hydro. And then we'll include, of course, the root of our polyatomic ion, but we have to change the suffix. And so the suffix changes. If it ends in ate, we change it into ick. And if it ends in ite, we change it into us. And so since this is nitrate, it ends in ate, so we're going to cross that out, and we put ick in its place. And then, of course, because it's an acid, we want people to know it's an acid. Acids are dangerous and reactive, after all, so we always include the word acid at the end of its name. And so this would be nitric acid is the correct name for this compound. Okay, I'll open the floor back up to any other questions or topics that you'd like to cover. No worries. Well, until somebody thinks of something in particular that they'd like to go over, I'm going to pop back over to that practice test that I had worked up. Now, there are going to be other topics on the exam that are not covered on this. You can find the exhaustive list of topics on the study guide. Just in case one of you hasn't seen the study guide yet, let me go ahead and show you where you can find that. It's going to be in modules. And then we're going to scroll down to the current module. And there it is, Exam 1 Study Guide. I've also included a HonorLock test quiz here, just so that you guys can test out your HonorLock, your webcam, and all that stuff to make sure that your computer is compatible, your web browser works, all of that good stuff. It's a lot easier for us to diagnose issues in this quiz that is worth no points than it is to diagnose them once the exam timer has started ticking down. So you might want to try that out if you find the time before our exam due date. Okay, back over here though. So we're going to start with nomenclature. The most important thing when you are doing nomenclature is to first categorize what type of compound you have, because we have different rules for naming different types of compounds. The three major types of compounds that we go over in General Chemistry 1 are going to be our ionic compounds, our covalent/molecular compounds, two words that mean the same thing, and then we have, of course, our acids, which we just went over. In order to identify each of them, you should really look at what elements they contain, and then based on those elements, look at your periodic table and figure out what type of compound it is. So here, PCl5, I'll pop over to the periodic table. Looking for P. P is right here. This is in the nonmetals. The upper right-hand corner of our periodic table is all of the nonmetals. There's kind of an imaginary line from boron down through to this ununoctium compound. And this imaginary line here is called the semimetal line. And so all of these compounds are semimetals, and everything above and to the right of those are our nonmetals. So here, phosphorus is a nonmetal and chlorine is a nonmetal. Combinations of two different nonmetals will always make a covalent compound. So unless it's one of the rare exceptions that it's an acid, which will show dissolved in water with the aqueous symbol, you should always name combinations of two nonmetals as covalent. To name our covalent compounds, we want to specify how many of each there are with the Greek prefixes. Greek prefixes we use in our daily lives. I feel like they're relatively commonplace, even if you haven't called them the Greek prefixes specifically. They are mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. Hopefully some of those sounded familiar to you. If not, it is one of those things I do expect you to know for our exam, so just write them on a flashcard and say them out loud a couple of times. I'm sure it'll come to you quickly. The one exception to using those prefixes is that for the first element, you do not have to specify that there is only one of them, and so we will not say monophosphorus here. We'll just say phosphorus. So this becomes phosphorus, and then we will include a Greek prefix before the chlorine atoms there. There are 5 of them, and so penta, and then chlor, we include the root name of our element, and then we are going to substitute the suffix. Chlorine usually ends in ine, that's the suffix for it, and so we'll swap that with ide. This is common for all of our chemical compound names. You always end in ide unless it's an acid. Okay, so phosphorus pentachloride is the name of this compound. We already named nitric acid earlier, but just to briefly rehash, the H in front and the aqueous at the end is enough to tell me that this is an acidic compound. We would look at all of the other elements here, NO3. I know this is a polyatomic ion because it's a part of an acid that has more than 2 elements in it, and so I'll go over to my polyatomic ion list here. I'll find the NO3-. It is called nitrate, and then we drop the suffix ate in favor of ic acid. This compound should be named nitric acid. Here we're given a chemical name already. This is the chlorite anion. That ite suffix is something we only see for polyatomic ions. And so this is a clue that you should go look at that polyatomic ion table. I'm going to be looking for chlorite, and here it is, ClO2-. And so this is really just a referencing exercise. ClO2 and minus. Next up, we have calcium chloride. So calcium, despite it being what makes up most of our bones, is actually a metal. We can find calcium over here in group 2. These are the alkaline earth metals. So because we have a metal combined with a nonmetal, our nonmetal, of course, being the chloride ion here, that tells me that we have an ionic compound. Ionic compounds are named by just writing out the formula is found by just writing the chemical symbols in the correct ratio. In order to find that correct ratio, we have to figure out what the ionic charge is. So again, back to our periodic table. Calcium here is the second column. Everything in the first column makes a +1 charge. Everything in the second column makes a +2 charge. And so calcium must be a 2+ ion. Ca2+. For finding the charge of our anions, or the negatively charged ions, we do a similar approach, but we don't start with -1 being the last column. Instead, -1 is the second to last column. We'll go over why that is in more detail later this semester, but for now, just remember that group 17/7a, the second to last group, is -1, and then as you move further to the left, it becomes -2, -3, -4, before moving back to being positive values again. So, chloride makes a -1 charge. So I'll write that like so, Cl-. What we're trying to do is figure out how many of each of these ions is going to go into our chemical formula. One quick trick that we can do is we can take the superscript of each, so that is the charge of each, and kind of swap it so that it becomes the subscript, or the number of each. So the 1- here just becomes a 1, so Ca. We imply the 1. You're not supposed to draw that 1 out, and so we leave it blank there. And then Cl, I have that 2+ moved down there, and so there's 2 of these. The reason that that trick works is because what we're trying to do is find a quantity of each ion that will create a neutral compound in the end. Calcium has 2 positive charges. Chloride has 1 negative charge. I don't want to add more than 1 calcium here, or else the charge will run away in the positive direction, so I want more than 1 chloride to counterbalance it. I'll need 2 of those negative charges to balance the 2 positive charges, and that's why I have CaCl2. The 2 chlorides balance the 2 positives from the calcium. And so here we would simply put CaCl2. Hydroiodic acid. I'm noticing, of course, that this is an acid, and so it starts with a hydrogen, I know that much. The number of hydrogens will depend on the charge of the other element. I see iode there, that must be iodine. So we'll pop over to our periodic table. I see that iodine is in group 17/7a, and everything in this group makes a 1- charge. Because it's all going to be that 1- charge, and since hydrogen makes a +1 charge, it's going to be in a 1-to-1 ratio. So I'll include the iodine. Now, you might be tempted to find a polyatomic ion that matches this. In fact, there are polyatomic ions with iodine in them if you look at your table here. Or actually, I guess this one doesn't include them. That's fine. Because we're not actually supposed to make this a polyatomic ion. The way we know this is supposed to be a binary acid is because of the word hydro in front here. Hydro always indicates a binary acid. Binary means 2 things. One of those things has to be hydrogen, therefore the other thing must be iodine. And this is, of course, going to be aqueous as well because all of our acids are dissolved in water. I'm pretty sure on the exam I was very specific about whether you should or should not include the aqueous symbol there. I'm going to guess that I wrote it to not include the aqueous symbol when you're typing it in. I will include it on the exam for you to see that it's an acid, but you don't have to include it as part of your answer. Moving on. Please, again, feel free to stop me at any point, guys. Potassium carbonate. Oh, I just said it out loud, didn't I? Whoops. Well, the way that I arrived at that conclusion is I see that there are more than 2 elements here. That's usually an indicator that one of these things must be a polyatomic ion. So I'm going to go ahead and look for a polyatomic ion that matches the CO3 there. Over here, we can see CO3 2- is the carbonate polyatomic ion. And so I'll put carbonate down as part of my name. Now, the first element in a ionic compound always just says its name. You don't have to modify the suffix for any of our cations / positively charged elements. Therefore, we'll just write potassium here. And therefore, potassium carbonate is the correct name. Moving on, I see CuCl2. In order to name this, I want to look at my periodic table and figure out what type of material copper is, what type of material chloride is. Chloride is a nonmetal, but copper here we see is a metal, and actually it's a special type of metal. This is a transition metal. Our transition metals can make a variety of different charges. We're not able to determine just based on their group what charge they should have, and therefore we have to infer the charge based on the other element present, in this case the Cl. Because chloride makes a 1- charge, I'll be able to do a little bit of calculation to determine the charge on the copper. So it's CuCl2. Each chloride here, so I have two Cl minuses, each one of those has a -1 charge. And so when I'm thinking about this, I'm trying to figure out what value for x can I put here to balance the two -1 charges. Well, +2. And so the correct charge for copper here is 2+. The way that translates into its name is we have to specify the charge of the metal in parentheses using Roman numerals. So we'll write out the name of the element first, copper, and then open parentheses. To write Roman numeral 2, I'll just do capital I, close parentheses. You're supposed to include a space in between the parentheses and then your anion, and then chloride is the same everywhere. You just call it, you just take the INE of chlorine and replace it with IDE. We don't have to specify how many chlorides there are here because we already did imply it with the Roman numeral 2 on copper. I find that this is a very common mistake students will make. They will look at the number of chlorides and say, great, this is copper 2 dichloride. But we don't want to be redundant in chemistry, so make sure you only use the Roman numeral 2 to specify the number of chlorides. Okay. I'm going to change this one slightly, actually. There we go. TiO2. It works out the same way in the end. It's just... Sorry, is there a question, Logan?
Yes, sir. What do you do if you have two transition metals?
You don't. It will never happen. Not in my class, anyway. Sorry if that was too reductive of an answer. You always are going to have a combination of a metal and a non-metal. It is technically possible for some more complex compounds. In particular, zeolites do this a lot, where you can have a variety of transition and main group metals as part of like a larger framework material. But we're just dealing with the basics here. So, TiO2, the titanium is another transition metal. We see it right here in group 4. You might be tempted to say this is, well, it's group 4, so it's got to be a 4+, but we can't say for certain until we analyze the charge of our nonmetal. The nonmetal in question was oxygen, and so oxygen is right here. I can count the number of spaces from group 17. So this is going to be 1-. That means oxygen must be 2-. So that's where we'll start when solving this one. We have, trying to write with the wrong side of my pen, TIX, some value is going to go up there. And then O, we have 2 of those oxygens because the formula was TiO2. So we have 2O and it's 2-. In order to figure out the number of positive charges, we need to think, okay, well, how many negatives do I have? I have 2 of the 2 minus here, and that's a grand total of 4 negatives. Since I only have 1 titanium, I must have a 4 plus charge on that titanium to balance all of the charges from the oxygens. Therefore, it is Ti 4 plus as my transition metal cation, and we have the 2O2 2 minuses, oh sorry, 2O 2 minuses as the anions. In order to convert this into a chemical name, we'll just call it titanium. Remember, the first element always just keeps its name. We open a parentheses. Roman numeral 4, you start with the I and then the V, close parentheses, and then oxygen becomes oxide. Aluminum sulfide. I see aluminum right here. This is a main group metal. It is 1, 2, 3 groups from the beginning of the row, and therefore we'll just make a 3 plus charge. And then sulfide is right here. It's a non-metal that makes a 2 minus charge because -1, -2. So we have Al3 plus and S2 minus. The reason I needed to determine what their charges are is because that's going to tell me how many of each element I need to create a neutral compound. We can try that swapping trick, and that's usually a pretty quick way to arrive at our answer, Al2, S3. We can double check that that math works out. 2 aluminums is going to give me 6 positives, and then 3 sulfurs is 3 times the 2 minus there. That's going to give me 6 negatives, which when we add those together is going to be 0, so this is a happy neutral compound. Al2S3 is therefore the correct chemical formula.
I have a question.
Yes, ma'am.
So, can you explain again, like when we would use the Roman numerals, or when we use like the penta, hexa and stuff like that?
Absolutely. So for the Greek prefixes, the pentahexa, stuff like that, those are used exclusively when we have 2 nonmetals together, and that's it. So in the case shown above, PCl5, phosphorus is a nonmetal. It's right here. And then Cl, also a nonmetal. Nonmetal plus nonmetal, use the Greek prefixes. You need the Roman numerals when you're using a transition metal, that is one of these here, or the next row down also, or the row below that, etc. Anything that's inside of this kind of rectangle here, you need to use those Roman numerals, and then you don't need to use any Roman numerals or the Greek prefixes when you have a main group metal ionic compound. And so that is lithium and down, beryllium and down, and then any of the metals over on this far right square. Did that answer
Thank
your?
you.
Yeah. No worries. Okay. We were almost finished with the nomenclature. Finally, we have BaClO3 2. Now, this can get a little bit tricky sometimes. Notice that we have a parenthetical statement here that has multiple atoms inside of it. This is your clue that this is a polyatomic ion. We are saying that we have multiples of this group of atoms. So, in this case, ClO3, we're going to take a look at our list of polyatomic ions. ClO3 is chlorate, ClO3 minus right there, the chlorate polyatomic ion. And so that'll be the second part of this name. And then the Ba there, we want to make sure that's not a transition metal. And it isn't. There's barium right there, so we don't need to use any parentheses in our chemical name. Therefore, this is simply barium chlorate. Any other questions on nomenclature? Any topics that you'd like reiterated, other example problems, anything like that?
I have one question.
Okay.
So, could you go over and explain like the difference between "ite" and "eight"? Because I know there's a difference. Like it has to be less, I think like less oxygen or something like that.
That's exactly correct. Yeah. So I'm not asking you all to memorize these, or even worse, to be able to infer what the name should be from the polyatomic ion. It is a little bit of a tricky concept. That's why I give you the table here. Don't ask you to memorize it. Ate and ite often will appear with the same root element to specify more and less oxygens, respectively. Ate means it's the higher number of oxygens. Ite means it is the lower number of oxygens. But again, you can see them here. NO3 minus, that's nitrate. NO2 minus, nitrite. I don't expect you to have those memorized. You can also see some more rare use of prefixes in polyatomic ions. The prefix per means the most of something, and hypo means the least of something. And so perchlorate, the chlorate tells you it has above the median number of oxygens. Per tells you it has the most oxygens chlorine could possibly entertain. And then on the flip side there, we have hypochlorite. Chlorite, the ite suffix there, tells us that it is below the median number of oxygens. And hypo, like hypodermic needle, it is underneath even that lower number of oxygens. So that's why it's just one oxygen on chlorite, or hypochlorite. So that's the short version of how we arrive at the ate versus the ite, but not a skill you're required to do for this exam.
Okay, thank you.
Yeah, of course. Great questions, guys. Let me keep moving here. So these will be a lot quicker. I just want to clarify, I think there is some confusion sometimes with what counts as what here. A pure substance, the word substance is very, very broad. It can be anything that is just chemically pure. When I say chemically, I mean if you were to describe it using that symbolic domain of chemistry, it would just be one, collection of atoms and numbers. You wouldn't have to put a plus. You wouldn't have to list multiple things. So H2O, water, is a great example of a pure substance. You could also include sugar as an example of a pure substance. You could include oxygen as an example of a pure substance. So they can be elements, they can be compounds, they could be ionic, they could be molecular. Any of that is fine. What you can't do for a pure substance is have any mixtures. So mixtures are where you're combining two or more different chemical compounds together, either in big chunks or in very finely divided, imperceptible size pieces. So, for example, if you listed air as a pure substance, that would be incorrect. Air is a combination of many different elements and compounds all dissolved in each other, swirling around really quick. It all seems the same to us, but it is multiple compounds. Okay. A compound is anything that is a pure chemical substance that is not an element. And so this has to be multiple elements combined together to create a new thing. You cannot list things like O2 as an example of a compound. A compound specifically must be two or more different elements. Homogeneous mixture, this is what I was describing with air. It is something that is imperceptibly different, but is still different. It is a combination of multiple pieces. A good example here would be iced tea, right? Minus the ice, I suppose. Or, any kind of beverage where you've dissolved sugar. I should say coffee. Coffee is probably a better example of this. There's 100,000 different compounds probably in your cup of coffee, but you can't really tell. You can't see the individual compounds. Therefore, since all of the coffee looks identical, we call it a homogeneous mixture. A solution is just another name for homogeneous mixture. And then finally, heterogeneous. This is anything where you can see the chunks. You can tell there are two or more different pieces combined together into this mixture. Classic example is wet sand. You can see there's some wet bits. You can see some seashells. And of course, you see the sand too. Because of that, it's considered heterogeneous. So basically, if you can see the difference with your eyes, it's heterogeneous. If you can't see the difference with your eyes, we class it as homogeneous. Okay. Complete the following arithmetic operations. Account for significant figures in your final answer. I've made these a little bit trickier than I want to, so we're just going to do a little swap-a-rooney there. Excellent. Okay. So whenever you are adding or subtracting different values and want to keep your significant figures, the rule is that you always keep the fewest number of decimal places. In order to keep the fewest number of decimal places for this sum, 18.6 minus 3.02, the calculator tells me 18.6 minus 3.02, that the answer should be 15.58. But because I'm keeping the fewest number of decimal places there, I would have to round that 8 up to the next digit. However, I don't want to do the rounding just yet because I have another mathematical operation I want to do inside the same problem. Anytime you round prematurely, you do something called propagating your error. You bring your errors from that initial rounding step into future rounding steps. So whenever you're doing math and chemistry, try and do all your calculations in one go, and then account for significant figures in your final answer. So I'm leaving the 15.58 the way it looks in my calculator right now, and then I'm adding the 4.007 to that. Gives me 19.587, and this is where I will round so that I only have the one significant figure, or sorry, the one decimal point. So it's 19.587. I'm keeping just this one decimal place here because that's the rule when you add and subtract numbers. And so I'm evaluating whether this is greater or less than 5. It is, of course, greater than 5. Therefore, I round my 5 up. That means that my answer, accounting for significant figures, should be 19.6. Any questions? All right.
Do significant figures happen to have a rule around rounding fives?
They do have a rule for rounding fives, yes. I don't really expect you all to know that rule. Just in case it ever comes up, I would give you points for rounding it in either direction because it is a little bit confusing in science. You're always supposed to round it in whichever direction makes the next digit even. And so if you were trying to round, we'll say 1.5 to have 2 sig figs, then the 5 is going to go up. That's how we do it classically in mathematics. However, so that would become 12. If you had 10.5 and you wanted to keep those same 2 sig figs, then the 5 actually rounds down to become 10.
So it's just keeping the even number then?
Yes, that's correct.
Okay.
All right. So for this next one, because we are multiplying and dividing things, we want to keep the fewest number of significant figures as our final answer. So the lowest number of sig figs in this problem is 3 here, the 2.11. So what I'm going to do is just plug and chug in the calculator. 9.843 times 2.11 gives me 20 point some large decimal, it doesn't really matter, divided by 1.248, an even uglier looking decimal, but I just need to keep 3 sig figs here. So the calculator says 16.6 something. I guess 64, it still matters there, 16.64. And so the 4 is going to round down because it's lower than 5. that means that my answer, accounting for significant figures, is 16.6. It is 3 sig figs once again here. Any questions? All right. Let's go ahead and we'll side by side with the periodic table a little bit, because we got to go back and forth quite a bit here. Number of electrons in argon. So, in order to find the number of electrons in an element, you have to know which of the numbers on our periodic table corresponds to the number of electrons. It turns out none of them directly, but one of them does indirectly, and it's the atomic number. In a neutral element, which we assume all elements on the periodic table are neutral in this form, the number of protons is equal to the number of electrons. Since the number of protons is the atomic number, we can very easily assume that argon has 18 electrons. Please feel free to stop me at any point if any of these rules or explanations don't make sense. The atomic number of phosphorus. Once again, we just have to recognize what an atomic number is. It's this upper left-hand number. So that's going to be 15 for phosphorus. Most likely charge of a potassium cation. So cations are positively charged. One of the ways that I've always remembered that is the word cation has a plus sign in it when you write it with my terrible handwriting. So that's one easy way to remember it. I had a student a couple of semesters ago tell me that you can always tell it's a cation because it's positive. That works a little bit better if you could see me doing the little kitty paw mime, but I don't have my camera turned on right now. So yeah, either of those rules works. We're making a positive charge here. And we're looking for potassium. Potassium's a group 1 element. Group 1 elements make a +1 charge, or I should say 1 plus. Number of neutrons in a sulfur, 34, 2 minus anion. So a lot of information contained there. Sulfur 34. That 34 is what we call the mass number. Not the atomic mass. That's a different concept. The atomic mass is what's shown at the bottom of each of the element boxes on our periodic table. This is a weighted average of all of the different isotopes based on their relative abundance here on Earth. And so looking at oxygen being 15.999, you might assume that, yeah, most oxygen is oxygen 16, and then a very, very small portion of it might be oxygen 15. Often the math is more complicated, but that's what it means. So this is the mass number. It's the number of protons plus the number of neutrons in sulfur. So in order to find the number of neutrons, I need to be able to find the number of protons. The number of protons in sulfur is just given right here on the periodic table. If I could get the comment box to go away, there we go. Sulfur has 16 protons. So I'll do 34 minus 16. And that's because the mass number minus number of protons is equal to the number of neutrons. In this case, that means the number of neutrons is 18. You might be asking, but Dr. Ayad, what about that 2 minus anion thing there? I just felt like trying to trick some students. Of course, that's not going to happen to any of you, my best students who are attending the review session. Okay. Most likely charge of an oxygen anion. Anions are the opposite of cations. Since cations are positive, anions must be negative. Oxygen is this element right here. It is two columns away from the noble gases here. Noble gases always have a charge of 0. The halogens is a 1 minus, and then that means oxygen and its group are all 2 minus. So the most likely charge of an oxygen anion should be 2 minus. Number of protons in nickel. Once again, just find nickel, 28. Number of electrons in a uranium 6+ cation. in order to figure this out, we have to find uranium. It's way down here in the actinide series. If you haven't put this together yet, the heavier the element is, the more likely it is to be radioactive. So anytime you're dealing with any of the radioactive stuff, want to find on your periodic table, usually look to the very last row. So uranium right here, it has 92 protons, which means it usually has 92 electrons. I say usually because anytime you have a cation, that means you have removed some number of electrons, leaving an excess of protons behind. So we started with 92 electrons. We subtracted 6 of them. I can tell because there's a 6 plus surplus there. So we'll subtract the 6 electrons that we used to create that charge, and that leaves us with 86 electrons. And then finally, the atomic mass of chlorine. Atomic mass, that's the value given at the bottom here. So this is just making sure you understand what the word atomic mass means. You should write 35.453 if asked something similar. Questions on using the periodic table as a reference?
Are the
Okey-doke.
charges going to be on the periodic table, or is this just the one we're using?
This is the exact periodic table you're using. I don't give you the charges. You'll have to be able to infer them based on the group number. There are a variety of tricks in order to do that. I always just count the number of spaces. The first column is always going to be +1, and then +2, etc. And then working in reverse, the first column is always going to be 0, and then fluorine is 1 minus, oxygen's 2 minus, nitrogen's 3 minus. There are more complicated and specific rules based on group numbers if you'd like to memorize those instead. But I've gotten by okay just counting the number of spaces.
So would columns 13 and 14 not be 4 and 5?
It does get a little bit more complicated because it's very, very challenging to create very large charges. And so usually instead of, column 14 being 4 minus and then column 13 being 5 minus, instead these don't really want that many electrons. Instead, they would prefer to make positive charges at that point. Carbon is kind of ambivalent. I've seen carbon make +4 and -4 charges, same with everything in its group. But boron doesn't really like to have a negative charge. It would much rather give away 3 electrons than it would rather gain 5 electrons. There is a rule that explains that. We'll get to it in chapter 6.
Understood.
Okay, great question. Very forward thinking. I like it. Okay, I do want to be able to refer to different groups of the periodic table by their names from time to time, so I expect you guys to learn these 5 groups at least. So the halogens, this is group 17, everything in that 17th column there, or 7A, whatever. Any of those names is fine. We'll do chlorine. It's a classic. Alkaline earth metals. You do have to be careful because there's 2 that sound very similar here. We have alkaline and alkali. Alkaline earth metals, the more complicated name comes second. It's group 2 here. So you can select any of those. We'll go with barium. Transition metals. The transition metals are that big rectangle of elements in the middle of the periodic table. You can choose any of those that you'd like. We're going to go with iron here. Well, I guess I did say using its atomic symbol, so I'll be more accurate then based on what was asked. FeClBa. Noble gases. The noble gases are our last column of the periodic table on the far right. We're going to go with xenon here. And alkali metals, any of the group 1 metals. Lately, lithium-ion batteries have been all the rage, so we'll do Li. Okay. This next question should seem pretty familiar. It comes from your homework, just different numbers in here. Element Q has atomic number 35, mass 79, and a 1 minus charge. Notice on your periodic table there is no element Q. That's why I've used this as kind of like a stand-in for like some random element. If its atomic number is 35, that is the same as the number of protons it has. With the number of protons and its mass number, we should be able to find the number of neutrons it has. So we'll do that one first because that's where my brain went. We'll take 79, and we'll subtract the number of protons, 35, and that's going to give us 44 neutrons. Then, to find the number of electrons, we also need the number of protons once again, 35. This is normally also the number of electrons, but I do see we have a -1 charge. That -1 charge means we have an excess of 1 electron. And so 36 is therefore the correct number of electrons. It has 1 more electron than the number of protons. We're going to skip this one because it's a little bit long and silly. It's more of the same skill we've been doing. But I do want to show you guys exactly how I would like you to use dimensional analysis. I think that this is a skill that eludes a lot of my online classes because they don't get to see me solving the problems on a regular basis. And it's not, dimensional analysis isn't there to make your life more challenging. It's there to make it easier. I feel like that sounds a little cliched as a professor telling you, oh, I'm just here to make your lives better. But really, dimensional analysis is a systematic framework for solving these rather complicated questions. Looking at this, we have scientific notation, we have unit conversions, we have huge numbers of miles. It can get kind of overwhelming, and it's really, really easy to drop a decimal or a comma or flip one of your signs upside down on accident when trying to solve these if you do it in a piecemeal fashion. Instead, I try to set them up as one big long string of numbers with units attached, and in that way, I can't possibly leave anything out because I'm checking my work with my units as I go through and solve. So, to begin, I like to collect all of my conversion factors at the beginning. A conversion factor is anything that is going to allow me to change from one unit into another. Typically, these are represented as ratios. And so here I can see 0.621 miles in a kilometer. That's miles per kilometer, so that's one of my conversion factors. I'll write that down off to the side in the format we're going to use it in the problem. So 0.621 mi is the symbol for miles per 1 km. And I do recommend writing it exactly like this. Next, I see meters per second. That's another good conversion factor. So 3.00 times 10 to the 8th meters is just the lowercase m per s for second. Let's see. We're trying to, by the way, I haven't even read the problem yet. That's how I actually solve these. The words are scary to a lot of students. I just go straight for the numbers. I'm seeing now that we're trying to convert between miles and hours. So aside from just the conversion factors that were given in the problem, sometimes I will ask you to use some common sense conversion factors. Some of you might be able to convert seconds into hours directly, but I think a more easy way to think of it would be, okay, I know that there are 60 seconds per 1 minute, and I also know that there are 60 minutes per 1 hour. And so now that should be all the conversion factors I need to get from my starting point, miles, all the way to the number of hours it'll take. When setting this up, I want to make sure that I include my units and that I'm canceling something every step of the way. You'll probably be given something that is a lone unit, something that isn't part of a conversion factor. In this case, it was 391,400,000 miles. And so that miles is what we'll be writing down first. 391,400,000, mi. Just keeping the symbolism consistent here. Now, I like to do the x as a symbol for multiplication. Some of you who have taken chemistry previously have seen this format instead, where you're going to fill in the blanks of these little grid lines here. Either is fine. I'm just doing it the way I was taught. Feel free to do it the way you were taught if you've taken chemistry previously. So I'm doing times, and I want to make miles cancel. You're always trying to make one thing cancel for every step that you write down. In order to make miles cancel, I know that miles needs to end up on the bottom here. I see this conversion factor right here. I'll put 0.621 miles down there and 1 km up top. And to confirm that I have canceled it correctly, I put a little slash through it. Don't scribble things out. You don't want to hide the information from yourself or from the professor grading it. Instead, you want to just show, okay, I have accounted for this miles. It has canceled. We now have number of kilometers. Technically speaking, you could solve at this point. You'd have a number of kilometers, and then you'd need to do different steps. However, we can set this up as one long continuous equation, which is my preferred way of doing it. So we've got 1 km up top. I'm going to multiply by something that makes kilometers go away. Whoops, I don't actually have a conversion factor that does that. Instead, I see meters over here as the next logical step in converting it into hours. Therefore, I need to come up with a different conversion factor. In this case, we need something that's going to go from km to m. That k prefix is kilo, and it means 1,000 of something. So another conversion factor we had to come up with ourselves here is that there are 1,000 meters per 1 km, kilometer. Now I can use this conversion factor as my next step. 1,000 meters per 1 km. Kilometers cancels with kilometers. Now I want meters to cancel. I'll do 1 second per 3.00 times, times 10 to the 8th meters. So meters cancels with meters. We'll deal with the scientific notation towards the end. Seconds, I can make go away using this term here. 1 minute on the top, 60 seconds on the bottom. The magic of technology. Okay. And then for the last step here, to go from minutes into hours, we know that there's 1 hour for every 60 minutes. Going back through, canceling seconds with seconds, minutes with minutes, to check our work. Before we call this problem done, we just want to make sure that all of our units have been canceled, except for the one our question asks for. In this case, we're asked how many hours will it take to reach Earth, and that's all we have left is hours here. Now I actually pull out the calculator and solve this thing. So on my calculator, I guess I can try and pull it up here so you guys can see exactly what I'm doing. You are permitted, and in fact encouraged, to use a handheld calculator on the exam. It's just so much easier when you have to do big, long problems like this. So we have 391,400,000 divided by 0.621 times 1,000. So you see, even on your handheld calculators, you can still put it in exactly the way I'm doing it here. If something appears on the bottom, I do divided by. If it appears on the numerator, I do times. And then divided by, now I don't want to mess with scientific notation on this, Windows calculator here. So what I'll do is I'll just expand this 3.00 times 10 to the 8th. To do that by hand, it's 3.00, and then that times 10 to the 8th means you just move the decimal 8 times. So 1, 2, 3, 4, 5, 6, 7, 8, and then I fill in those zeros. So comma, and then comma. And so 3.00 times 10 to the 8th is the same thing as 300 million. And so then this value divided by 300,000,000, and then divided by 60, and then divided by 60 again. And then I hit enter, and we find the exact amount of time. So at the speed of light, it takes a little bit more than a half an hour for the signal to reach Earth. To keep the correct number of significant figures here, we assume that any conversion factor is an exact number. It's an exact value, so we don't worry about those sig figs. For example, the number of miles is defined as 0.621 of a kilometer. Like that is, like scientifically we said that's how much a mile is. So the only value here that's actually measured is the first one, the distance between Earth and Jupiter. Don't ask me how they measured it. It'd be a really, really long tape measure. But I can see that we have 1, 2, 3, 4 significant figures. These trailing zeros don't count as significant because they come before any decimal points. If you had a decimal point and then some zeros after it, then all of the zeros become significant. But in this case, insignificant zeros. So we just need to keep 4 significant figures here, which means that my final answer should be, oh, I had it here, is equal to 0.5836 hours. Please make sure you include units. Any questions on dimensional analysis?
Are we going to be given a chart with any of the conversions, or should we have those memorized?
You will be given them in the problem, or they will be what I call common sense conversions. I expect you all to be able to go from milli and kilo to the base unit. A milli, like a millimeter or a milliliter, is 1/1000th of the base unit, and then a kilo of anything is 1,000 of the base unit. I'm not going to worry you guys about using the megas and femtos and all those other weird, tiny or gigantic ones. Even though some of them are like kind of commonplace, really I just want the basics from you guys. Milli and kilo, memorize those. And it's just 1,000th or 1,000. And then any other conversion factor will be given to you. In this problem, it was kind of a rare case because I had seconds and hours in there, but I do figure that you guys can do seconds to hours conversions.
Word. Thank you.
Yep, of course. Great questions. That is the conclusion of the material I prepared to help you guys study. Are there any other chemistry topics you want to cover? If there aren't, I am going to just briefly run down how I expect the test taking to go for you guys. It's a little bit tricky, especially if you haven't used honor lock before. So, questions going once? And going twice.
You have some questions about the design of the test.
Okay, go for it.
Are you allowed to tell us how many questions there are going to be?
I would be allowed. I do not remember. I mean, if it's really important to you, I can stop sharing my screen here.
What other sections besides what you've shown us on the practice exam should we look for?
I feel like the practice exam is pretty good. I wrote this exam last semester. Let me just double check that there isn't anything glaring missing from it. Oh, and you know what? I gotta stop the recording.